Hello everyone, welcome to the fourth lecture of the course Mathematical Aspects of Biomedical Electronic System Design. In this lecture, we will cover discrete time Fourier transform, properties of Fourier transform, connection with LTI systems, Fourier transform of periodic signals. Moreover, we will also introduce sampling and we will see sampling theorem. Okay, so let us begin with the lecture. We will start with defining discrete time Fourier transforms. Recall that discrete time Fourier series are defined only for periodic signals. However, like continuous time Fourier transform, discrete time Fourier transform, in short DTFT, are also defined for aperiodic signals. Let us say what these are. DTFT is for a discrete time signal. Xn is defined as, Xn is a discrete time signal. Its DTFT is defined as x e raised to j omega equal to, and from minus infinity to infinity, xn e raised to minus j omega n. Notice that unlike continuous time Fourier transform, where we used x omega to denote Fourier transform, here we are using a slightly different notation. I am calling DTFT x e raised to j omega. So this notation is different from continuous time Fourier transform. There is a feature that distinguishes this discrete time Fourier transform from continuous time, and that is these Fourier transforms are periodic. So what I mean that x e raised to j omega is periodic with period 2 pi. So x e raised to j omega plus 2 pi is equal to x e raised to j omega. This is something that's can be easily verified by using the definition of Fourier transform. As in continuous time case, this equation is called analysis equation. Let us see a few examples. Example 1 is where xn is Dirac delta function, that is, it is delta n. Then what about x e raised to j omega? If we just apply the definition, it becomes n equals to minus infinity to infinity del n e raised to minus j omega n, which in turn is equal to 1. Let's see another example. Now I take xn to be equal to a n u n, where a has absolute value less than 1. Now let's see what DTFT is. X e raised to j omega is equal to, since un is 0, for all negative n, I can start the summation from 0. N equals to 0 to infinity a n e raised to minus j omega n, which becomes n equals to 0 to infinity a e raised to minus j omega whole raised to n, and it's a geometric series which turns out to be 1 over 1 minus a e raised to minus j omega. Let's see one more example. Now my xn is 1 if mod n is less than or equal to capital N, and it's 0 otherwise. So if I plot this signal, it would look like follows. 1 2 3 dot 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 up to n. Here -1 -2 -3 dot 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 up to -n. The signal is 1 at all these points, and it's 0 outside this. Okay, so what about the Fourier transform of this signal? Let's see. X e raised to j omega. Now I only need to sum from -n to n, e raised to minus j omega n, because the value is 1 in this range, and if we solve, it's easy to do. It turns out to be sine omega n plus half divided by sine omega by 2, if omega is not equal to 0, and it's simply 2n plus 1 if omega is 0. Okay, so having seen these examples, the next question is, if we are given Fourier transform of a signal, how can we retrieve the signal from this Fourier transform? So that is, how do we obtain so-called inverse Fourier transform of a signal? Okay, so let's see. Just like continuous time case, we use synthesis equation for this purpose. So next we are looking at inverse Fourier transform. So for a signal, for a Fourier transform x e raised to j omega, its inverse is obtained using the following equations. Xn is 1 over 2 pi integral over 2 pi x e raised to j omega, e raised to j omega and d omega. Okay, so as in continuous time case, this equation is called synthesis equation. Again, notice one difference vis-a-vis continuous time case, that is, the synthesis equation requires integration only over one period. Notice that 2 pi was the period of the Fourier transform. So synthesis equation requires integration over only one period of dtft. Let us see an example. Suppose x e raised to j omega is a periodic pulse function. So that is x e raised to j omega is the following function. It's a function that takes value 1 between minus omega c and omega c, and where omega c is less than pi, so pi will be somewhere here, and then this pulse repeats. It's 2 pi and so on. So what about the inverse Fourier transform of this? How do we obtain xn? As said above, we only need to integrate in the range over one period. So here we can do it by integrating from minus omega c to omega c. Okay, so let's see, minus omega c to omega c, and in this range the value is 1. So I have e raised to j omega 1 t omega, and at the front we have 1 over 2 pi. If we solve it, it turns out to be 1 over pi n 1 over 2j e raised to j omega cn minus e raised to minus j omega cn, which we can readily recognize to be sine omega cn. So the signal is sine omega cn divided by pi n. Okay, fine. So now, having seen the inverse Fourier transform as well, we will now look at a few properties of discrete time Fourier transform. While stating these properties, I'll use the same convention that I used for continuous time case, that is, for any function and its Fourier transform pair, I'll use the following notation. Xn is the signal and its Fourier transform is x e raised to j omega. So this is signal DTFT pair. Okay, so with this convention, let us look at properties of DTFT. The first property that we will see is time and frequency shift. We will see that all these properties are counterparts of similar properties in continuous time case. So similar duality observation holds here as well. Time and frequency shift. Okay, so if xn has Fourier transform x e raised to j omega, then the time shift property says that Fourier transform of x n minus n naught will be e raised to minus j omega n naught x e raised to j omega. Similarly, the frequency shift property says that Fourier transform of e raised to j omega naught n xn will be x e raised to j omega minus omega naught. Okay, let's see a special case of the frequency shift property, which is often of interest. Special case. Here I set omega to be equal to pi. Notice that e raised to j pi n is minus 1 raised to n. Thus, from the above frequency shift property, we get that Fourier transform of minus 1 raised to n xn is x e raised to j omega minus pi. Okay, so these were time and frequency shift properties. The next property that we will see is time expansion property. Expansion property. Before I state the time expansion property, let me define what is meant by an expanded signal. Okay, so for any non-zero integer m, say m equals to plus minus 1 plus minus 2 plus minus 3 etc. So the signal xmn defined as xn by m if n is equal to 0 plus minus m plus minus 2m etc. and 0 otherwise. Well, so xmn is non-zero only if n by m is an integer. Let us see an illustration of this. So let's say my xn is as follows. Then the expanded signal, say twice expanded signal x2n will look like as follows. So it will have non-zero values only at even values of n. Right? So I will have this. At all other positions its value will be 0. Now time expansion property says that if xn has Fourier transform x e raised to j omega, then xmn will have Fourier transform x e raised to j omega m. Okay. Again, a special case of this property that is quite useful is what we call time reversal property. Time reversal. This is a special case where capital M is -1. Now, time reversal property says that Fourier transform of x minus n will be x e raised to minus j omega. Okay, so let's see an example illustrating Fourier illustrating time reversal. Let us consider xn equals to a raised to minus n u minus n, where as before the absolute value of a is less than 1. We have readily seen that the Fourier transform of a raised to n u n is 1 over 1 minus a e raised to minus j omega. So using time reversal property, Fourier transform of xn will be 1 over 1 minus a. Now minus j omega will be replaced with plus j omega. Minus omega will be replaced with plus omega. Okay. So this is an use of time reversal property. After time reversal property, time expansion property, the next one is linearity property. So number 3 is linearity property. Okay, so this property is similar to its counterpart in continuous time case. For instance, let us assume that x1n has discrete time Fourier transform x1 e raised to j omega, and x2n has discrete time Fourier transform x2 e raised to j omega. Then linearity property says that for some numbers a and b, a x1n plus b x2n will have Fourier transform a x1 e raised to j omega plus b x2 e raised to j omega. Okay. Let's see an illustration of this property with an example. So let us say that let's say that we want to evaluate Fourier transform of xn equals to a modulus of n, where again modulus of a is less than 1. Observe that, so what we want is x e raised to j omega. Observe that xn can be decomposed as a n un plus a minus n un, right, minus delta n. Now we know the Fourier transforms of each of these. Notice that we just computed the Fourier transform of, so this is a, this is a, we just computed Fourier transform of a minus n un. We had earlier computed Fourier transforms of a n un and delta n respectively. So x e raised to j omega can be obtained by combining appropriately combining the Fourier transform of the individual functions. So it becomes 1 divided by 1 minus a e raised to minus j omega plus 1 over 1 minus a e raised to j omega plus minus 1, right? And this can be simplified to be equal to 1 minus a square divided by 1 plus a square minus 2a cos omega. I will skip the details, but it's something that it can be easily seen. Okay. So this was an illustration of the linearity property. Next we look at conjugation and conjugate symmetry properties. Conjugation and conjugate symmetry properties. Okay, it says that if xn has Fourier transform x e raised to j omega, then the complex conjugate of xn, that is x star n, will have Fourier transform given by x star e raised to minus j omega. Okay, so this has several implications. For instance, if xn is real valued, then we know that xn is equal to x star n, and so the above relation implies that x star e raised to minus j omega is x e raised to j omega. We can combine this property along with the time reversal property to get many interesting results. In fact, if we use periodicity of x e raised to j omega, then we observe that this can further be written as x e raised to, we see that what we can write is the following: x e raised to j omega is equal to x star e raised to j 2 pi minus omega. Okay, and this is using periodicity of x e raised to j omega, and this equality has couple of implications, namely the absolute value of x e raised to j omega is equal to absolute value of x star e raised to j 2 pi minus omega, which in turn will be same as absolute value of x e raised to j 2 pi minus omega. Moreover, the angle of x e raised to j omega will be equal to negative of the angle of x e raised to j 2 pi minus omega. So both these properties now follow from periodicity of x e raised to j omega. We can combine the conjugate symmetry property with time reversal property to get interesting inferences. For instance, if xn is xn is real, then xn is equal to x star n. We have readily seen that x star e j omega is equal to x minus e j omega. Moreover, if xn is even symmetric, that is xn is equal to x minus n, then x e raised to e j omega is equal to x e raised to minus j omega. Okay, now if we combine these two properties, we see that if xn is real and even symmetric, then x star e raised to j omega is same as x e raised to j omega. That is, x e raised to j omega is real. We can follow similar arguments to claim that if xn is real and odd symmetric. What do I mean by odd symmetric? X minus n is minus of xn for all n. So if xn is real and odd symmetric, then x star of e raised to j omega is equal to minus x e raised to j omega. In other words, in this case, x e raised to j omega is pure imaginary, is purely imaginary. So these were conjugation and conjugate symmetry properties. The next property that we will see are differentiation or difference properties. Differentiation or difference properties slash difference properties. Okay, so there are two properties here. One is frequency differentiation property. Okay. So first property is frequency differentiation. Which says that if xn has discrete time Fourier transform x e raised to j omega, then nxn will have discrete time Fourier transform which is j d derivative of x e raised to j omega with respect to omega. Okay. Notice that in time domain we are talking of discrete time, so there cannot be an analogous differentiation in time property, but we can talk of a time difference property, namely we can talk of Fourier transform of xn minus xn minus 1. Alright, so from the time shift property we see that Fourier transform of xn minus 1 is 1 minus e raised to minus j omega x e raised to j omega, and this property is called time difference property. Time difference property. We will see uses of these properties in a while, but for now let us look at the next property, which is Parseval's relation. This is similar to the relation in case of continuous time signals. In particular, we have that n equals to minus infinity to infinity modulus of xn whole square is equal to 1 over 2 pi x e raised to j omega modulus square d omega. Again, notice that on the right hand side the integration is limited to one period only. Okay. Next property is multiplication property. Okay. This says that if x1n has Fourier transform x1 e raised to j omega and x2n has Fourier transform x2 e raised to j omega, then the product of these two signals, that is x1n times x2n, will have Fourier transform which will be 1 over 2 pi x1 e raised to j theta, x2 e raised to j omega minus theta d theta. Notice that the integral on the right hand side remains of convolution. However, this time this operation is called periodic convolution, because the integrand is periodic and integration is over one period. So this is called periodic convolution. Okay. Let's now go to the next property, which is very important property, and we will see several uses of it, and this is convolution property. Convolution properties. Okay. This property says that the Fourier transform of convolution of x1 and x2, that is x1 star x2 of n, its Fourier transform is simply product of individual Fourier transforms, that is x1 e raised to j omega times x2 e raised to j omega. Okay, we will now see several examples or applications of this property. So we will show in the first example, we will show how we can use this convolution property to calculate convolution of two signals. So computing convolution. So let us assume that x1n is alpha n un, where modulus of alpha is less than 1, and x2n is beta n un, where again modulus of beta is less than 1. We have already seen that x1n will have Fourier transform 1 over 1 minus alpha e raised to minus j omega, and x2n has Fourier transform 1 over 1 minus beta e raised to minus j omega. Now from convolution property, the convolution of x1 and x2 is nothing but inverse Fourier transform of multiplication of the terms on the right hand side. That is, we would be interested in computing the inverse Fourier transform of, let's say this is x1 e raised to j omega and this is x2 e raised to j omega. Then our interest is in computing the inverse Fourier transform of this product. That is 1 minus alpha e raised to minus j omega, 1 minus beta e raised to minus j omega. Like in the similar example, for continuous time case, we can use partial fraction expansion to simplify the right hand side to get it in a convenient form. So let us say that this is equal to a divided by 1 minus alpha e raised to minus j omega plus b divided by 1 minus beta e raised to minus j omega. We can solve this partial fraction expansion to get a alpha plus b beta, rather a beta plus b alpha to be equal to 0 and a plus b to be equal to 1. And on solving, we get a equal to alpha divided by alpha minus beta and b equal to beta divided by alpha minus beta, rather minus beta divided by alpha minus beta. This says that convolution of x1 and x2 is alpha over alpha minus beta alpha raised to n un minus beta divided by alpha minus beta beta raised to n un, which in turn can be written as 1 over alpha minus beta alpha n plus 1 minus beta n plus 1 the whole times un. Let's see another example where We cannot use simple partial fraction expansion, but I use convolution property in conjugation with differentiation in frequency property to compute convolution. Okay. So again I consider xn to be equal to alpha e raised, I take xn to be equal to alpha raised to n un, where modulus of alpha is less than 1, and now my interest is in computing convolution of x with itself. Okay, so this is what I am interested in. Towards that, I'll start with recognizing that discrete time Fourier transform of this convolved signal is x e raised to j omega whole square, which is 1 over 1 minus e alpha e raised to minus j omega whole square, which can be seen to be e raised to j omega over alpha j d over d omega 1 over 1 minus alpha e raised to minus j omega. Right? Notice that this is d over d omega x e raised to minus j omega. This will help us in proceeding further. Okay. Now before we take the inverse Fourier transform, let us notice that Fourier transform of nxn will be j times derivative of x1 e raised to x e raised to j omega d omega, which is j d over d omega 1 over 1 minus alpha e raised to minus j omega. Okay. Now but notice that the terms here on the right hand side in this equation are quite different from this. That is, I see an additional e raised to j omega. This is where I'll invoke time shift property. So this was differentiation property. Differentiation. To be precise, frequency differentiation. Now I'll invoke time shift property to notice that Fourier transform of xn plus 1 will be equal to e raised to j omega times this term. So it will be e raised to j omega times j times d over d omega 1 over 1 minus alpha e raised to minus j omega. Say this is star. Now I can compare this right hand side with star to recognize that the inverse Fourier transform of x1 e raised to j omega whole square is, that is x star x, the convolution of x with itself is 1 over alpha n plus 1 x n plus 1. Okay. By substituting the value of xn, which is alpha raised to n un, I see that the right hand side becomes alpha n plus 1 un plus 1. So this becomes equal to alpha n plus 1 un plus 1. Notice that this is same as n un, because only point where the two could differ was n equals to minus 1, but at n equals to minus 1 both of these functions are 0. So this can be written as alpha n un. Okay. So we see how we use several properties to compute the convolution of x with itself. So this was all about the properties of discrete time Fourier transform. Now we will see how we can use this convolution property to compute the frequency response of a discrete time LTI system. Okay, so this is yet another application of discrete time Fourier transform, and this is in computing frequency response of response of discrete time LTI system. Okay. Notice that a discrete time LTI system is characterized by the equation, difference equation, k equals to 0 to n ak yn minus k equal to k equals to 0 to m bk x n minus k. Now we'll substitute xn equals to delta n and yn equals to hn, that is impulse response, to obtain k equals to 0 to n ak h n minus k equals to k equals to 0 to m bk del n minus k. Notice that we did so because by definition when we input delta n to this LTI system, the output yn is equal to hn. So it was perfectly valid to substitute xn equals to delta n and yn equals to hn. Okay. Now taking Fourier transform of both the sides, we find that k equals to 0 to n ak e raised to minus j omega k h e raised to j omega, where h e raised to j omega is Fourier transform of hn, and we have used time shift property here. This becomes equal to k equals to 0 to m bk e raised to minus j omega k. Okay, this says that h e raised to j omega is equal to k equals to 0 to m bk e raised to minus j omega k divided by k equals to 0 to n ak e raised to minus j omega k. We will now give a couple of examples to illustrate how we can use this relation to compute impulse response of a discrete time LTI system. So let's see examples. So first example is, say yn is input and output of the discrete time system as related as follows: yn minus 3 by 4, yn minus 1 plus 1 by 8, yn minus 2 is equal to 2xn. Question is, what is impulse response of the system? Let us observe that in this system a0 is 1, a1 is minus 3 by 4, a2 is 1 by 8 and ak is 0 for all other k. Similarly, b0 is 2, b1 equals to b2 equals to 0, bk is 0 for all k greater than 2 as well. Hence, from the above relation, we can see that h e raised to j omega is given by 2 divided by 1 minus 3 by 4 e raised to minus j omega plus 1 by 8 e raised to minus 2 j omega, which can further be written as 1 minus half e raised to minus j omega times 1 minus 1 by 4 e raised to minus j omega. We can use partial fraction expansion to see that the right hand side is equal to 4 by 1 minus half e raised to minus j omega minus 2 divided by 1 minus 4 e raised to minus j omega. Now we can easily compute the inverse Fourier transform of the two terms on the right hand side to obtain hn equals to 4 into half power n un minus 2 into 1 by 4 raised to n un. Okay, let's see another example. Now we are given an LTI system whose impulse response is Hn equals to alpha n un, where modulus of alpha is less than 1. So we have an LTI system which impulse response Hn is as given here, and we need to find a relation between input and output of the system. Okay. Notice that h e raised to j omega, that is Fourier transform of the impulse response, also called frequency response, is 1 over 1 minus alpha e raised to minus j omega. If we compare this expression of frequency response with the general relation that we had earlier derived, let's say star, then we find that A naught is equal to 1, A1 is minus alpha, B naught is equal to 1, B1 is 0, and so on. And thus we can say that input and output are related as yn minus alpha, yn minus 1 is equal to xn. So we see how we could use discrete time Fourier transform to get a relation between input and output of the system when the impulse response of the system is known. Okay. Now let us take a step back, as we did in the case of continuous time case, and see what are the conditions under which the infinite sum defining discrete time Fourier transform is well defined. Okay. So that is, let us recall that discrete time Fourier transform of a signal xn is given by k equals to minus infinity to infinity xk e raised to minus j omega k. Now we are asking the question, is it that the sum on the right hand side, the infinite sum on the right hand side, always defined? What are the conditions that we can put on xt to ensure that this sum is always defined? Recall that we had a condition, we had a sufficient condition in the case of continuous time Fourier transforms. We get a similar condition here as well. Okay, so let's see what that condition is. The infinite series defining DTFT is guaranteed to converge if n equals to minus infinity to infinity summation of absolute value of xn is finite. However, notice that this is a sufficient condition, not necessary. Several of the examples that we saw earlier, for instance, xn equals to delta n, or xn equals to an un, a raised to n un, where modulus of a is less than 1, satisfy this condition. But there are many other signals of interest for which this condition is not satisfied. What do we do in that case? Notice that, recall that in the case of continuous time Fourier transforms, we introduced a notion of generalized Fourier transforms to handle that such cases. Even now we can develop, even in this case we introduce the notion of generalized Fourier transforms to deal with the cases where signals are not absolutely integrable. So this condition is called when the signals are not absolutely summable. So this condition is called absolute summability. Absolute summability. For instance, let us take a few cases where the signals are not absolutely summable, not absolutely summable signals. As I said, in this case we will talk of generalized Fourier transform, generalized DTFT. So let's say xn is equal to constant, that is 1 for all n. In this case, it turns out that the generalized Fourier transform of xn, that is x e raised to j omega, is equal to 2 pi k equals to minus infinity to infinity delta, which is Dirac delta function, omega minus 2 pi k. This relation can be easily verified using synthesis equation. So if I just substitute x e raised to j omega in the synthesis equation, I get xn equal to 1 for all n. This is the equation. Okay. Similarly, if xn is raised to if xn is equal to e raised to j omega naught n, now since I know the Fourier transform of xn equal to 1, I can use the time shift property to infer that now since I know the Fourier transform of xn equal to 1, I can use the frequency shift property to infer that Fourier transform of this xn, x e raised to j omega, is 2 pi k from minus infinity to infinity delta function at omega minus omega naught minus 2 pi k. Okay. We can use this property, this star, let's say double star, we can use this property double star along with linearity property to compute the Fourier transform of periodic signals. Let's see how it is done. So Fourier transform of periodic signals. So let us say xn is a discrete time signal which is periodic with period n, such that I can write the discrete time Fourier series for xn as k equals to 0 to n minus 1 ak e raised to jk 2 pi by n small n. Then the Fourier transform of xn can be computed using linearity as follows: x e raised to j omega is equal to 2 pi I equals to minus infinity to infinity k equals to 0 to n minus 1 ak del omega minus omega naught minus 2 pi. Now instead of ak delta of omega. Notice that instead of omega naught I'll have here k 2 pi by n minus 2 pi I, and this can be simplified to be equal to 2 pi k equals to minus infinity to infinity ak delta omega minus 2 pi by n k. This simplification is not straightforward and it involves a few steps. I'll skip those in the interest of time. This completes our discussion of Fourier transform for discrete time signals. Next we will look at the notion of sampling. Suppose we have a continuous time signal xt for instance, say this is xt and say we sample it every t units of time. This t, 2t, 3t, 4t, and we take these samples. So we sample it every t units of time. Sample it every t units of time. The question is, can we reconstruct xt from the samples? Can we reconstruct xt from the samples? Which are x and t and in z plus, that is n equals to 0, 1, 2, 3, 4 etc. Okay, this is the question whose answer is given by sampling theorem by Shannon and Nyquist. So here is the answer. Sampling theorem by Shannon and Nyquist. These gentlemen have shown that the answer is affirmative, that is we can indeed retrieve xt if the following conditions are met. First condition is xt is band limited. That is its Fourier transform x omega is 0 for all omega greater than omega m for some omega m greater than 0. Okay. The second condition is the sampling frequency say omega s, which is 2 pi by t, is greater than 2 omega m. Okay. So this is twice the bandwidth of the signal that is being sampled. And the third condition is use a scale and time shifted sinc function is being used for reconstruction, for interpolation. A scale and a time shifted sinc function is used for interpolation. More precisely, we obtain the interpolated signal, say xrt, as n equals to minus infinity to infinity xnt sinc t minus nt divided by capital T. Okay, so this is shifted as well as scaled sinc function. Okay. Notice that each sinc function in the summation on the right hand side is centered at a sample point. Moreover, if we evaluate the right hand side at the sample points, then the value returned is same as the value of the original function at the sample points. In other words, if I compute say xrmt, which is n equals to minus infinity to infinity xnt sinc m minus nt divided by t, so here t get cancelled, then this is equal to 1 if m is n and 0 otherwise. So the value of xrmt becomes nothing but xmt. Okay, so clearly the original signal and reconstructed signal agree on the sample points. The interesting feature of sampling theorem is ensures that the two signals match each other at all the points. So here is the formal statement of the theorem. It says that if x omega is 0 for all omega that are either less than minus omega m or greater than omega m, and 2 pi over t is, which is equal to sampling frequency. So if if omega s equal to 2 pi over t is greater than 2 omega m, then xrt as given by above equation, let's call this star as we will refer to it again and again, then xrt is equal to xt for all t. Okay. While we will not see the formal proof of the sampling theorem in this lecture, I will explain a few key ingredients that lead to this theorem. So here are key ingredients. Okay. Let us first observe that the signal xrt, reconstructed signal xrt, can be viewed as output of an LTI system with input xpt and output and impulse response HRT. Where xpt is equal to n equals to minus infinity to infinity x and t del t minus nt, and HRT is sinc t by capital T. So what we claim is that xrt is convolution of xpt and HRT. So to see the properties of xrt, let us see these two signals individually. Okay. So first we will see xpt. It can be seen that xpt itself can be written as product of two signals xt and pt, where pt is equal to n equals to minus infinity to infinity del t minus nt. Notice that this pt is an impulse train. It's a periodic signal, and so the xpt is called impulse train sampled signal. It's called impulse train sampled signal. Further notice that pt is a periodic signal, and we can write its Fourier transform using the theory that we have learned earlier to be the following. So pt Fourier transform is, let's say p omega is 2 pi by t, k equals to minus infinity to infinity del omega minus k 2 pi by t, which is omega s. Moreover, I can use the convolution property of Fourier transform to compute xp omega to be equal to 1 over t, k equals to minus infinity to infinity x j omega minus k omega s. Notice that xp omega is nothing but scaled sum of shifted copies of x omega. So what I mean is that if my x omega is like this, so this is minus wm, and if omega is greater than 2 wm, then xp omega would indeed look like this, where this is omega s is 0 minus omega s, and this is 1 by t, whereas this was 1. Okay. And if the peak value of x omega was 1, peak value of xp omega will be 1 by t. Okay. Now let us shift focus to HRT. Recall that HRT was sinc t over capital T, and so its Fourier transform will be simply the pulse signal with width w omega s. This peak value is t. This is my x hr omega. Now, since xrt was convolution of hrt and xpt, so its Fourier transform will be simply hr omega times xp omega. If we observe the two Fourier transforms on the right hand side, you will notice that xp omega, you will notice that xr omega is same as x omega, right? Which means that if we reconstruct, which means that the reconstructed signal xrt is equal to xt. Okay. Notice that if omega s is less than 2 omega m, then the copies of x omega in xp omega, they overlap. For instance, for the above example, we get a signal that looks something of this sort. When the copies overlap, the low pass filter outputs a signal that differs from the original signal. Low pass filter outputs a signal that is different from the original signal. This phenomena is referred to as aliasing. We now see a couple of examples that illustrate this phenomena of aliasing. So here is example 1, which is xt equals to cos omega naught t. In this case, notice that x omega will be just 2 impulses at minus omega naught and omega naught, each with amplitude pi. Moreover, xp omega will be sum of shifted version of these impulses. So I get this is xp omega, this is minus omega naught. In this case, the reconstruction filter, that is HR omega, would look like this. So this is between minus omega s by 2 to omega s by 2, and we see that the reconstructed signal will have Fourier transform with 2 pulses exactly as the original signal, sorry, with 2 impulses exactly as the original signal, and so there is no aliasing in this case, and xrt is equal to xt. Let's now look at another example where now xt is cos omega naught t as before, but omega s is 3 omega naught by 2, which is less than 2 omega naught. Okay. In this case, xpt will be as follows. So we have minus omega naught, and then the shifted version of this, but those shifted versions will be like this. So this is one shifted version, this is another shifted version. Okay, so this value is omega s minus omega naught, this one is again minus omega s plus omega naught, and so on, and this will be minus omega s by 2, this will be omega s by 2, and in this case, if we employ a low pass filter, the reconstructed signals Fourier transform will not be same as the original signals Fourier transform. In fact, reconstructed signals Fourier transform will be this. So this pulsage will be at omega s minus omega naught, which is omega naught by 2, and similarly here at minus omega naught by 2 respectively. And so xrt is equal to cos omega naught by 2t, which is not same as xt. So this illustrates the phenomena of aliasing. Now there is one question that remains. What if omega s is equal to 2 omega m? We will give an example that will say that setting omega s equal to omega m does not suffice. That is, we will not be able to reconstruct the signal, in particular when x of omega m is not equal to 0. So we may not reconstruct the signal spatially, okay, if x omega is not equal to 0 at omega equals to omega m. Let us see it with an example. So let us consider xt to be equal to sine omega naught t in this case. Notice that x omega will be as follows. This is omega naught, this is plus omega naught. These amplitudes as before are pi and minus pi respectively. Now in this case, if I use omega s to be equal to 2 omega naught, in this case xp omega will be obtained as follows. I will draw copies of x omega. So this is x omega. Here is the next copy. At each point xp omega is nothing but sum of all these signals. See that the two pulses at all the points neutralize each other because they have same amplitude but opposite signs. So xp omega is 0 for all omega. Clearly in this case we cannot recover, or we cannot reconstruct xt from xpt. This brings us to the end of the module on signals and systems. In the next lecture, we will begin with few topics in linear algebra. Thank you.